Quantum thermodynamics combines two of the most successful physical theories, quantum mechanics and thermodynamics. It investigates thermodynamic quantities such as temperature, heat and entropy in systems that exhibit quantum behavior such as superposition and entanglement. Traditional thermodynamics played a crucial role in the Industrial Revolution. And similarly, I expect quantum thermodynamics to make important contributions to emerging quantum technologies. Here, in the Quantum Thermodynamics group at the University of Basel, we want to understand the useful tasks that can be performed by open quantum systems. These tasks include refrigeration, generating electric power from heat, keeping time, and many more. Taking a thermodynamic approach allows us to better understand the required resources as well as how efficiently they are consumed. In our daily work, we develop new theoretical methods to describe open quantum systems, we derive novel relations that govern their behavior, and we make predictions for state-of-the-art experiments.
The physics of this ball can very well be described by classical or Newtonian physics, and we can eventually also try to describe it with quantum mechanics, and we can do that, nothing impedes us, but in reality this would not make this object quantum. This would just restate that the features that make quantum mechanics special do not appear in such a high temperature and macroscopic object. Nowadays, we are at a point in the development of technology that we can actually fabricate devices that operate in very small scales and cold temperatures, which means that unavoidably we have quantum mechanics creeping in. And we want to understand in the performance of these devices whether we have to go a bit around some of these special features of quantum mechanics, or even more importantly, if we can use these features for some enhancement. In one of the projects of my PhD here in the Quantum Thermodynamics group, we tackle part of this puzzle. We consider a miniaturized version of a thermoelectric engine in which we have a hot reservoir, a cold reservoir, and our system of interest in the middle. The heat driven across our system of interest leads to some power being extracted, and this heat is carried in the form of photons. These photons are known to behave as both particles and waves in the quantum domain, and they drive these Cooper pairs jumping across the system, which generates some electric current. So we try to understand what are the relevant features of this wave-particle duality in this quantum heat engine. And in particular, we look at the average power being extracted and its fluctuations. And we show that the average power doesn't care whether we describe the system with a wave, particle or quantum model, whilst the fluctuations of power, they are really sensible to this wave-particle duality, in the sense that the power fluctuations capture important quantum features such as vacuum fluctuations and the effects of quantum coherence.
As a PhD student in our research group, I currently work on an approach to determine the response of a quantum system subject to an external signal. More formally, I work on a path integral-based approach to input-output theory, which means we use methods from quantum field theory, usually used in the context of high-energy physics, to determine the response of a quantum system, for example, to a laser. As is usually done in quantum field theory, we employ diagrammatics to make the lengthy calculations appearing there more tractable and more intuitive. This diagram right here, for example, is part of the probability of a photon being created at the output. Here, two photons enter, interact, and then one of them leaves and goes to the output port. The exact answer for this probability would comprise infinitely many of these interactions. But quite often you can get really close to the exact answer by considering those with only a few interactions. Later on, we would like to make this approach here into a useful tool to tackle problems in input-output theory which so far have not been manageable. With that, we hope to give a tool to other researchers as well to treat problems in input-output theory.